Hello, math humans. We're going to do 1.4a today. We're going to have a discussion about continuity. So we are going to determine continuity at a point, and then on an open interval and on a closed interval. A very important thing in math is to answer the question that's asked. And so in relation to what we're doing today, if they ask about continuity, then you have to make a statement about f of x is continuous, and then you would proceed to say where that happens. If you're asked to talk about discontinuity, that was rough, then you would write a statement f of x is discontinuous, and then you would say where that particular thing happens. So in calculus, especially on your exams, you always want to make sure that you answer the question that's asked. All right, so now let's define continuity. Continuity means that there are no breaks in the function. There are no holes, there are no jumps, and there are no breaks. Some people like to say if you can draw without lifting up your pen, then the function is continuous. So we would say a function is continuous at a point C if f of c is defined. So the function is continuous at a point C if the function is defined at point C. A function is also continuous if the limit of the function as x approaches C exists. And then the last thing that we would consider is that the limit of f of x as x approaches C is actually going to be f of c, which means, because remember, a limit can exist, but a value could be undefined. So therefore, if the function is defined, the limit exists, and the limit of the function evaluated at that point is the function evaluated at that point, then we know that the function is continuous. All right, so if we talk about continuous, then we also have to talk about discontinuous. T-I-N. For whatever reason, that's a hard word for me to spell. Whew. Discontinuity says if there are breaks, then there are two types of discontinuity. And I'm going to write D-I-S-C. Okay? We've talked about them briefly, but we're going to re-talk about them again. One is called removable discontinuity. And we've talked about this in previous math courses, but it basically means that a factor can be removed, and when it's removed, it creates a hole in the graph or in the function, okay? So it means that there is a point of discontinuity, and so an example would be, let's say the function is x squared minus 1 over x minus 1. I can factor this to be x plus 1 over x minus 1 over x minus 1. I can remove the factors. So there is a hole at x is equal to 1. This, what's left over, is just a cute little line with a y-intercept of 1. So it means that my graph would look like this, but when I get to x is equal to 1, there would be a hole or a point of discontinuity. The second type, let me go to another page, of discontinuity is called non-removable. And this is going to be your vertical asymptotes. So let's say I have f of x is equal to 1 over x. Remember that I have a vertical asymptote at x is equal to 0. It's non-removable because there's nothing that I can factor it with, so that means that the vertical asymptote stays in the graph, and so then I would have this situation. So non-removable means you basically can't take it out, it has to stay, and then that particular situation would create our vertical asymptote. All right, so again, I'm going to say it's very important, and I can't stress this enough, it's to answer the question that's asked. So you always, did I say always? Want to make sure that you answer the very specific question that's asked. So let me illustrate this. So let's say we go back to our point, g of x is x squared minus 1 over x minus 1, and this turned into x plus 1 times x minus 1 over x minus 1, and we removed that. But let's say the problem says, discuss the continuity. We know that we have a hole at x is equal to 1, but that is where the function is discontinuous, okay? So we would say g of x is, and there's a couple of different ways I can say this, continuous, U-O-U-S, everywhere, except when x is equal to 1, or we could say g of x is continuous over the domain, but if I say that, then I have to say that the domain would be a negative infinity to 1 unioned with 1 to positive infinity. So you could report it either way, but notice it didn't ask me to discuss the discontinuity, it says discuss the continuity. So then when I write my answer, then I have to specifically regurgitate the prompt. G of x is continuous, and then I say where the function is continuous. All right, let's start our example. So for the first example, I want to discuss the continuity. So this time we're going to have a piecewise function, and I'm going to have x plus 1 and x is less than or equal to 0, and x squared plus 1 and x is greater than 0. So this is actually kind of an interesting situation. So if I graph this, remember we learned how to do this in pre-calc. If I graph this function, this is a line, but it says x has to be less than or equal to 0, so it's the line that goes here. So I'm just going to draw it's the bottom half of the line, and this point is included on this piece. This one is x squared plus 1, which would be an x is greater than 0, but technically it's open, and it would be the right-hand side of the parabola. This particular piece opens a hole. This particular piece fills a hole. So therefore, f of x is continuous over all real numbers, okay? And let me show you another way to do that. So let's evaluate the function, and let's evaluate it at each piece, okay? So if I did 0 plus 1, I would get 0 plus 1 is equal to 1. And if I did 0 squared plus 1, I also get 1. Because the y values are the same, that's another way of verifying that the function is continuous. All right, the next concept that we're going to look at is called one-sided limits. My brain got a little bit ahead of where my hand was. All right, so when we talk about one-sided limits, there are some functions that don't have two sides. And so remember, we talked about the limit of a function as x approaches c is equal to L if and only if each of the limits from the particular side is equal to the limit of the function as x approaches c from the right. But what if we have this function? Okay, so this would be y is equal to the positive square root of x. There is no left-hand portion of the graph. So if I said, what is the limit of the function as x approaches 0, I can't take that limit because there's no left-hand side of the function. It does not exist. So then I would have to say, does not exist. But I could say the limit of f of x as x approaches 0 from the right, and then I would say that that is equal to 0. So a one-sided limit means that sometimes a function doesn't have another side, so I can consider that limit. All right, so for example number 2, I want to find the limit as x approaches a negative 2 from the right of 4 minus x squared. Okay? If you think about this graph, this is the top half of a circle, and so it's going to look like this. This is a negative 2, this is a positive 2, because remember for circles, x squared plus y squared as a y is equal to r squared. So y is equal to plus or minus r squared minus x squared. It's really kind of handy to remember that. So they've given me the top half of the circle. Well, if I approach the negative 2, right, I can come in from the right. I cannot come in from the left because there's no left-hand side of the graph. And so the only thing that I can talk about is the right-hand side. So then I would say the limit of this function as x approached a negative 2 from the right is equal to 0. So that's actually kind of easy. And I just did that with direct substitution. I also know what the graph looks like, so this was an easy value to come up with. All right, now let's talk about a limit on a closed interval. That's an I. Whew. All right, so let's say I have a graph, and it's just going to be a whoop, and it's only going to be a little piece of that, and this is A, and this is B. Alrighty, I guess it helps if I scoot it up. So I only have a portion of the graph from A to B. So I can say the limit of the function as x approaches A from the right is going to be f of A, and then the limit of the function as x approaches B from the left is going to be f of B. And both of these are one-sided limits. Oftentimes on a one-sided limit, it is helpful if you have a graph because that can help you manage what you're looking at when you consider the limit. The third example says, discuss the continuity. Remember, we always answer the question that's asked of f of x is equal to the square root of 1 minus x squared. And again, that's a cute little circle, right? It's the top half of the circle. It's helpful if we know our graph because 50% of your exam, when you take that in May, is going to be without a calculator. And so it's helpful if we understand some graphs so then I don't have to work quite as hard. Okay? So here's my graph. If I look at this graph, I'm going to say the domain is from a negative 1 to 1. And I know that f of a negative 1 is 0, and I know that f of 1 is also 0. So if I want to discuss the continuity, I can say that the limit of f of x as x approaches a negative 1 from the right is going to be 0, and the limit of the function as x approaches a positive 1 from the left is 0, then we can say f of x is continuous over its domain. And remember, I can't say a function is continuous over the domain unless I've previously defined the domain. And if you'll also notice, we've technically used the definition of a limit in a closed interval because if I evaluated the function at the two endpoints, then I considered the one one-sided limits, so therefore now I can show that the function is continuous over the domain. All right, example number 4 says find the x values at which f is not continuous, that's a C, and then classify the discontinuities. Ooh, that's a long word. All right, notice that there are 2 questions. There's 2 fingers. You can't see me holding those up. So because I have 2 questions, that means that I have to have 2 solutions. Always answer the questions that are asked. The function that we're going to be given is x minus 6 over x squared minus 36. Factoring is my favorite F word, so the first thing I'm going to do is rewrite this as x plus 6 and x minus 6. If we'll notice, the x minus 6 cancel, so I have a point of discontinuity at x is equal to 6, and that's going to be a hole. And then I have a vertical asymptote at x is equal to a negative 6. So my function has become 1 over x plus 6. Okay, so it says discuss where the function is not continuous. So I'm going to say f of x is discontinuous at x is equal to plus or minus 6. Notice this is the positive 6, that was the whole, and here's the negative 6. Then the second question, and this is what students often miss, is classify the discontinuities. X is equal to a negative 6 is a non-removable discontinuity. Saying that it's a hole is appropriate because it describes what happens to the graph, but this is the appropriate notation because that says what actually is the type of discontinuity. And then x is equal to 6 is a removable discontinuity. Okay, so this technically is the hole. I said it backwards, and this is the vertical asymptote. Though these are the features of the graph, this is what the classifications are. So you have to make sure that you don't talk about the graph's characteristics, but what the types of discontinuity are. All right, that is it for today. I will see you soon.